welcome to next session. In this session, we will solve way to heating fluid mechanics oxidation. First of all, one mark question. Question one: Rheological diagram of different type of fluid is shown in figure. Column one represents the nature of fluid, and column two represents the curve showing the variation of shear stress against shear strain rate. Column one Newtonian, two shear thinning, three shear thickening, four Buckingham plastic, column two MNOP. The most appropriate match between column one and column two is the Newtonian fluid is represented by this O. Okay. Newtonian fluid is represented by O. Okay. So one is corresponding to O. A and B. Okay. And shear thinning is by P. So Q is P. So answer is what? B. Shear thickening is by N and Bingham plastic is the N. Okay. So answer is B. Next, in a two-dimensional, incompressible, any-rotational flow, stream function psi is equal to psi is function of x and y, and velocity potential phi is equal to phi function of x and y. Exist velocities in x and y direction are non-zero, and product of dy by dx pi constant and dy by dx psi constant is uh, the slope as the stream function line and stream uh, as the velocity potential lines are perpendicular to each other, and the slope of the streamlines are v by u, and slope of equipotential line are minus u by v. So the product is your minus 1. So answer is your minus 1. Slope of this product is minus 1. Okay. So answer is next. The inviscid flow past a rotating circular cylinder can be generated by the superposition of uniform flow, doublet flow, and vortex flow. Okay. So this is theoretical question. You have to remember all these what the uniform flow and the bread forms, and what the uniform flow source and vertex forms. Okay. The velocity field and the surface normal vector are given by V is equal to Ui plus Vj and Wk, and N1I plus N2j plus Nck respectively. If Euler's equation are to be solved using boundary conditions that must be satisfied at the wall is option A V dot N 0 V 0 and delta dot V 0 V cross N 0. Okay. V dot N is your Vn cos theta. Okay. And the as any normal vector for cos 90 is 0. Okay. So angle dimension is 90. So cos 90 is 0. So it should be 0. And in other word, we can say that v dot n is your un1, sorry, vn1, vn2, and wn2, and no normal component of water flow into the valve. Okay. So this is the required condition that will allow the flow along the wall, not normal to the wall. Okay. Next, so answer is your v dot n 0 because dot product is cos theta b into magnitude of b magnitude of n into cos theta cos 90 is 0. The influence of the Claude number is most significant in capillary flows, crippling flows, free surface flows, and compressed flows. Answer is free surface flows. The Claude number is used to compare the wave making resistance between bodies and bodies size of different size. In free surface flow, the nature of the flow, supercritical or subcritical, whatever it is, depends upon the whether the Claude number is greater than or less than. Okay. So this is most widely used in open channel. Okay. So this so please set this here. Next, if the stream function psi is equal to xy for a two-dimensional incompressible flow field is given as 2y bracket x square minus y square, the corresponding velocity field is the, the stream function is given as this 2y. Okay. Now, in terms of stream function, we have velocity in exercise, curly cycle, curly right. So here, if you differentiate it, then it will be 2x square minus minus 2x square y cube, okay, we get y cube, and 6y square, okay, so, taking to a common x square minus 3y square. Now, v is here minus I by x, so differentiating it again, it will be 2 and with respect to x, okay, 2y or 4y(x), it will be 0 because there is no x in it. So minus 4xy. So psi is equal to 2x square ui minus vj. Okay, for vj plus vj and v is your minus 4xy. So answer is your B answer. 2x square minus 3y square I minus 4xyj. Option B is your next. Water is flowing in two different tubes of diameter d and capital 2D with the same velocity. The ratio of laminar friction factor for the larger diameter tube to smaller diameter tube is. So friction factor is your 64 by E. Okay, uh, for laminar flow. Okay, and the roll number is rho by D by mu. Okay, so friction factor becomes the 64 divided by rho by D. So when comparing two pipes having diameter D and 2D, okay, then the ratio factor is here F2D by FD. Here, this D comes out. When we take F2D, then 2D will be here, and then take D. Okay, so option 0.5 A is here 0.5. Option A is here. Next, the velocity field is V is equal to x y square I plus 4xy j meter per second. The vorticity of the fluid element in the field at x is equal to 1, y is equal to 2 in per second is. So V is your x y square I plus 4xy j. Okay, finding we have to find out the vorticity. So vorticity curly u by curly x. Oh, sorry, curly u by curly y minus curly u by curly x. And curly u by curly y is u is this quantity for x y square, so 2x y, and b is this quantity. So this is your 4y. So the verticity is the difference of the two. Okay, putting the values 4y minus 2xy and putting x is equal to 1 and y is equal to 2, we get 4 answer is there. Okay. Next. A Peters static tube is used to measure air velocity in a duct by an electric process. The density of air is 1.2 kg per meter cube. The difference between total and static pressure is 1 kPa. The velocity of air at measuring location in meter per second. So here the density of air is 1.2. Okay. And the difference between total and static pressure is 1 kPa. Okay. So it is dynamic pressure given by half rho u square. Okay. So this is kinetic head. Okay. Or kinetic pressure or dynamic head. Okay. So it is your 1 kPa or 1000 Pascal equal to half rho v square. So v is your 40.33 meter per second. Putting the values, rho is equal to 1. Next, 2 marks question. A parallel pipe of 2 meter into 2 meter square cross section has 10 meter in length and 10 meter in length. is partially floating in water up to depth of 1.2 meter, with its longest side being horizontal. Specific gravity of the block is A point at B, point 6 C, point 5 D, point 4. Okay. So volume of the propeller inside the battery is 2 meter into 2 meter. Okay. Or into 1.2. That is the volume of water because whatever volume of the propeller is in water, that is the volume of water. Volume of water is 2 into 10 to 1.2. Okay. Because 2 is its one dimension and 10 is other dimension. 1.2 is the depth that is inside the water. Okay. So this is the volume of the water displaced and the buoyant force is your weight of propeller inside the water. Buoyant force is your weight of the weight that is acting on the weight of the propeller is the buoyant force. Okay, or that will be equal to volume weight of the water space also. Okay, so volume of water space is 2 into 10 into 1.2. So this is 2 into 10 into 1.2, and weight of the propeller is 2 into 2 into 10. Total weight is uh, uh, volume of propeller into density propeller into G, and this is volume of water space into rho G. So that is the buoyant force. Okay, so W is acting in downward direction, and buoyant force is acting in upward direction. Both are, and no other force are acting. Okay, no other force is acting. So these forces balance each other. So your rho B by rho is 1.2 by 2. So that is why it's 6. So specific gravity of the block is your point 6. Okay, and specific gravity is defined by as the density of the substance divided by density of water. So it is ratio of this to this is point 6. Okay. Next, the velocity field in a two-dimensional unsteady flow is given by V is equal to V bracket x y t is equal to 2xy square I plus 3xy t j meter per second. The magnitude of acceleration of a fluid particle located at x is equal to 1 meter, y is equal to 1 meter, at the time t is equal to 1 second in meter per second scale is option A 16, option B is 18.1, option C 24.1, option D 34.1. So V here is your 2xy square I 3xy t. Okay. Now we have to find out magnitude of acceleration. So we will find out the component in x direction. Component of acceleration in x direction and component of acceleration in y direction, and then we will put x is equal to 1, y is equal to 1, and t is equal to 1. Okay, and then we will find the probability. So the acceleration in x direction is dv by dt, curly by curly x, curly x by curly t plus curly by curly y, curly by curly t, curly by curly t. So u is your this for t, 2xy square. So curly by curly x is your 2y square, and curly x by curly t is your 2xy square. Okay, and curly u by curly y is your uh, tx. Sorry, curly u by curly y is your 4xy, and curly y by curly t is your 3xyt. Here should be t. Here should be t also. So here, okay. So this is your ax. Putting x is equal to 1, y is equal to 1, t is equal to 1. We get ax as 4 and 12, 4 plus 12, 16. Now ay dy by dt, curly v by curly x, curly x by curly t, curly by curly t, and curly v by curly t. And curly v by curly x is your 3xyt or t by t. Okay. And curly x by curly t is your u is your 2xy square. and curly v by is your 3xt, and 3 by t is your 3x by t. Curly y by curly t is your v is your this one, 3x by t, and curly v by curly t is your curly v by curly t is 3x by curly v by 3x by, okay. Now putting again the value of y, t and x, that is 1 1 1, okay. So ay gets, we get ay as 18. The total acceleration will be ax square plus ay square root, so a is 24.1 meter per second. Our answer is C. So C answer. Next, in a two-dimensional incompressible any rotational flow, fluid velocity in y direction is given by v is equal to 2x minus 5y, and the velocity u in x direction is, so curly v by curly x, curly v by velocity in the two-dimensional, as the flow is incompressible and irrotational. Okay. Uh, so the continuity equation for incompressible flow and irrotationality for that flow should be satisfied. So for incompressible flow, curly y is equal to curly v by curly x. Okay, so curly v by curly y is your minus 5. Okay, so curly v by curly x will be 5. Okay, so or u is equal to integrating u is equal to 5x plus c. So this is equation number 1. This is for this is equation 2. And for irrotational flow, curly u by curly y should be equal to curly u by curly x. Okay, and from this curly u by curly y is 0, and curly v by curly x is also 0. Curly u by curly y, sorry, curly, this is only v, that is this is not v. Okay, so as u is not given, so curly u by, as v is given, so curly v by curly x is your 2. Okay, so curly v by curly u by curly y is your 2, because these are equal, or u is integrating u is 2y plus c1. Okay, so equating 2 and 3, sorry, now again differentiating curly by curly x is your, this is 0, and this is your curly c1 by curly x, because it is a function of x. So now equating 1 and 4, you can put curly by curly x as 5, so curly c1 by curly x is 5, so c1 is equal to 5x. Okay, so putting in equation number 3, putting the value of c1, so u is equal to 2y plus 5x, to answer is your C. So first you have to satisfy both the incompressibility equation and the rotational equation. That is, the incompressibility equation is curly by curly minus curly by curly x, and from this we get the curly by curly x and u. Okay, and then we satisfy the irrotational equation. So that is curly by curly y is equal to curly by curly x. So curly by curly y 2. Okay. Now equating this 1 and 4, okay, we get the constant C1, and we have the u in terms of C1. So putting the value of C1, we get u is equal to 2y plus x. Answer is C. Next, a two-dimensional laminar viscous fluid film of constant thickness H steadily flows down on incline as shown in the figure. Acceleration due to gravity is g. If the velocity profile in the fluid in the liquid film is given by u is equal to k by bracket 2h minus y, v is equal to 0, the value of constant k is. So this is the fluid flowing with the velocity profile is given as this, and height is h, and free stream velocity is called capital U. Okay, and u is the velocity at the distance, v is the gravity force, sorry, acceleration due to gravity, and this is angle theta, and vibration is here. So now first of all, we have to find out the, as u is varying as k by minus 2h minus y. Okay, so we have to find out the value of k in terms of rho, g, and quantity. Okay. So first of all, we find out the mass of the fluid flowing in this where. Okay, so at any distance the velocity u, sorry, at any distance, at any distance y, in a strip of thickness dy, the velocity u. Okay, so the mass flow rate is your rho u. Okay, rho u dy into distance perpendicular to the strip. Okay, so if the distance perpendicular to the strip or the width is unity, so we can write that the mass flowing through the strip is rho du by rho u dy. Okay, and y is varying from 0 to h. Okay, y is varying from 0 to h. So integrating to find out the mass. Okay, now u is this your ky as a function of y is ky minus 2h minus y. Putting this value, putting this value. Okay, so rho k, rho k by this is your 2h minus y square dy. Okay, so integrating 2hy square by 2 minus y cube by 3 at 0 limit. So it is h cube, h cube, and it is h cube by 3. Okay, so rho k, so it is rho k2 by 3 h cube. Okay, so this is the mass flow, mass flowing through this region that we can get by integrating. Okay, now if we multiply mass by g, then it is the rate flowing. Okay. Now to find out the shear stress, okay, to find out the shear stress, uh, we have this equation at any layer from the bottom. We have this equation now is equal to du by dy. Okay, and du by dy u is given, u is given as this value. Okay, so du we can get du by dy. So du by dy is your 2kh minus 2ky. Okay, so that is the shear stress at a distance y from the bottom. Okay, in a strip of thickness dy. Okay, the shear force. Uh, Now the shear force. This is the shear stress. Okay, now if we multiply the shear force by the respective area, then we can get the shear force. Okay, shear stress by respective area. Then we get the shear stress. And if we the respective area for the shear stress is your parallel to the shear stress, and parallel to the shear stress is your velocity component, and width is 1 unit. So the area per unit time is your du into w is 1. Okay, so it is tau to du. So this is the shear stress per unit width per unit second. Okay, and as the shear force uh, per unit width per second. Okay, or as it is acting on this on one layer. So if we integrate it, integrate within limit 0 to infinity, so then we can get the total shear force. Okay, so u is your this quantity ky 2h minus y. Okay, so du by dy is this. Okay, now putting du is equal to this value and changing the limits to 0 to h. Okay, as u is varying from 0 to infinity, and so and y is varying from 0 to h. So changing the limit. So this is the shear force, and by integrating it, we can get shear force. Okay, and this is a simple integration. Okay, open this k square h square k square y square minus 2k square h by. Okay, 0 to h limit. So then integrating k square h square by k square y cube by 3 minus 2k square y square by 2. Okay, so putting h 0. So this is your shear stress. Okay, so this is your shear stress. Okay, for nu k square h cube by 3. So shear stress as the water as the fluid is flowing in this direction, so the shear stress will act in this direction. Okay, and there may be some normal component also. Okay, but we are now concentrating on this also, on this. Okay, and weight is acting on and in this direction. Okay, So shear stress is acting, or shear force is acting in this direction, and weight is acting in this direction. Now balancing, resolving along this along the plane, we get Fs shear force is equal to W sin theta. Okay, so W is equal to, that we have found out, W is equal to 2/3 rho K H cube rho G. Okay, 2/3 rho K H cube. Okay, sin theta. Okay, now equating these two, and Fs is your, Fs is 4 mu K square H cube. Okay, so from this we have K is equal to rho G sin theta by 2 mu. Okay, so there are two things we need to find out K in terms of loading. First, we have to find out the weight of the fluid flowing per second per unit width, and then the shear force per unit width per unit per second. Okay, then vectorly solving it. Okay, so this is the shear force, this is W, and then solving it. Okay, the component of W in the direction is W sin theta. So answer is the rho G sin theta by 2 or option A. Okay. Next, a water jet of 100 diameter is spewing out of a nozzle at a speed of 50 meters per second, strike the vein and flows along it as shown in figure. The vein attached to the cart, which is moving at a constant speed of 20 meters per second on a frictionless track. The jet is deflected at an angle of 30 degrees. Take density of water as 1000 kg per meter cube, neglecting the friction between vane and the fluid. The magnitude of the force exerted by the water on the cart in x direction in Newton is. So this is the cart, okay, and its velocity is v c is equal to 20 meters per second, and the jet is moving with the jet is moving with 50 meters per second. Okay, and it strikes the card and gets deflected. Okay, and it's the deflection. 30 degrees. Okay, so mass of jet striking the vein is your, as jet is as the sorry, as the vein is moving with 20 meters per second, jet is velocity is 50 meters per second. So the relative velocity with which the jet is striking the this vein is 50 minus 20. That is uh, so the relative velocity is 50 minus 20. Okay, and mass and A is for the area of the jet, and rho is density water. Okay, so the mass striking the vein is rho A, relative velocity. Okay, okay. So this is your mass flow rate. Okay. Now uh, the jet being deflected by 30 degree. Okay. So drawing the inlet and lateral velocity diagram. Initially the velocity is V1, and this is the velocity card. So this is the relative velocity. Okay. So this is VR1. So V1 is your 50, V is your 20, and VR1 is your 30 meter per second. Okay. Now the now as the jet is being deflected by 30 degrees, so this is the relative velocity of the jet. Okay, that is VR2. Okay, and u is your, as u is in this direction. Okay, and vw2 is also in this direction. The relative velocity between them is vw2 minus u. Okay, so this is the outlet velocity diagram. Okay, so now from this diagram we have VR1 as 30 meter per second and V1 as 50 meter per second. Okay, so that is equal to VW1. Okay, so initially we have VW1 as V1. Okay, now finally we have to calculate that VW2. Okay, now as the relative velocity is not changing. Okay, there is no loss, no loss upon the striking, so the relative velocity will remain same. So VR1 is equal to VR2 and VR1 is equal to V1 minus U. Okay, so that is 30. So this is 30. Okay, so this is 30. VR1 is 30 and this angle is 30 and that is equal to VW1 minus U equal to VR2 cos 30. Okay, okay, cos 30. So VW2 is your VR2 cos 30 plus this U is your plus this U is your 20. Okay, so we can find out VW2 by solving this triangle. Okay, or now we have VW1 as this quantity that is 50 and VW2 as 45. Okay, so force on the jet is mass flow rate. Mass flow rate is this and change in velocity. So change in velocity is your VW1 is initial velocity and finally is VW2. VW2. So force on the jet is 947 and that is also the and according to the third law of Newton, the force exerted by the jet, force exerted by the cart on the jet is this. So the jet will exert same force on the cart. So the answer is here 947.08 Newton. So answer is 947. Next, the capillary waves are generated in a sea. The speed of propagation c of these waves is known to be function of density, wavelength, and surface tension. Assume rho and lambda to be constant. The surface tension is doubled. In the functional form, the relevant non-dimensional group percentage uh, increase in propagation speed is. So as these waves are the function of surface tension, so the non-dimensional number, Weber number should be the same for the two conditions. Okay, so according to first condition, the speed of propagation is c, and density is rho, wavelength is lambda, surface tension is sigma. So assume rho and lambda to be constant. Okay. Now in the second condition, rho and lambda are constant, and surface tension is double. Okay. So we have to find out the percentage increase in speed. Okay. So the Weber number is nothing but inertia force but tension force. So this is inertia force is rho a c square and tension surface tension force is sigma into wavelength. Okay. So your Weber number is sorry a is the area. So it is function of L square. So you can put it as lambda square. So now the non-dimensional Weber number becomes rho lambda t square by sigma. Okay. Now for two cases the Weber number should be same. So rho lambda t1 square by lambda. Okay. Then the surface is variable. So here we will go sigma. So rho lambda is same. Okay. And so velocity c2. So from the as these numbers are same. So Weber number should be same because we have to use one of the non-dimensional numbers. Okay. For the dynamics, for similarity, the Weber number should be same. Okay. So C2 square minus C2 square by C1 square should be equal to 2. Okay. So C2 by C1 is your root 2. So increase in speed is final speed is your root 2 C and initial speed is 1 C. That is 41.4%. Okay. Next, question number 16. Consider a fully developed two-dimensional steady flow of a viscous fluid between two fixed parallel plates separated by a distance 30 mm. Dynamic viscosity of fluid is 0.01 kilogram per meter per second, and pressure drop per unit length is 300 pascal per meter. The fluid velocity at a distance of 10 mm from the bottom plate in meter per second. So in a uh, laminar flow or fluid bed flow, within the plates, the velocity is at an instant at a distance y from one of the plates is given by this minus 1 by mu only p by dx p by minus t minus s. So this is the formula that we have to remember for the flow between the parallel plates. Okay. So here mu is just 0.01. Okay. And del p by dx is just 300. Okay. And thickness is 30 mm. Okay. And y is y we have to find out the velocity at that point. So y is what 10 mm. Okay. So putting these values, you can find out velocity. Okay, that is 3 meters per second. Okay. We have all the quantities mu 0.01 LP by dx 300. Okay. And t 30 mm, y 10 mm. Okay. So putting these values within that velocity here are all good. See? Next, a 2.6 gram smooth table tennis ping pong ball has a diameter of 13 mm. Density of air is 1.2 kg per meter cube. Neglect the effect of gravity taking coefficient of drag as 0.5. If the ball of the if ball is struck, if ball is struck with initial velocity of 30 meter per second and initial deceleration in meter per second is okay. Uh, so here the density of air is your 1.2. Okay, and mass of ball is 2.6. And velocity, initial velocity is your 30 meter per second. Okay. And diameter of the ball is 30 mm. Okay. So first of all, the air, as the ball is hit with the velocity of 30 meter per second, it will be suffered by the drag due to air. Okay. So the drag coefficient is also given, that is 0.5. Okay. So the drag force which is acting on the ball is here 0.5 into 1.2, sorry, CD into rho A U square by 2. Here A is the projected area of ball. So as ball is sphere, so projected area will be circle. So projected area will be pi by 4, 38 by 100 square. Okay, so U is your uh, U is 30. Okay, initial velocity 30, 30 by 30. So putting this, we are left drag force. Okay, so A being the retardation. Okay, retardation or deceleration. Okay, deceleration. Okay, so the total retarding force will be or inertia force will be ma. So putting as all of the retardation is done by the drag force, so we have to equate this force equal to drag force and then we find out the acceleration. Here m is your mass. Mass is your 2.6 gram or 2.6 by 1,000 kilogram. So by putting the values you can have A is equal to 117.713 meter per second. Next, on a flat plate transition from laminar to turbulent boundary layer occurred at a critical Reynolds number. The empirical relation for laminar and turbulent boundary layer thickness are given as given by lambda laminar by x is equal to 5.48 Rex is for minus zero point 0.5. Lambda turbulent by x is equal to 0.37 Rex minus zero point 0.2. Respectively, the ratio of laminar to turbulent boundary layer thickness at location of transition is zero point 0.3. The value of R critical is. So here the at transition both the laminar and turbulent boundary layer are of same thickness. Okay. So as for laminar boundary layer, the equation is this. For turbulent boundary layer, equation is this. Okay. So at suppose at a distance x, both the lambda and turbulent layer get same value. Okay. ratio of the uh, okay. The here given it is given the ratio of the lambda on the other side. Okay, at transition it will be same, but at location mm, x equal to 0.3. Sorry, at the ratio of the lambda to the thickness at location of transition. Okay. The ratio of sorry, the ratio of lambda to tubular boundary layer thickness at the transition location is 0.3. Okay, so let x be the location of transition. So delta lambda by delta tubular is equal to 0.3. Okay, so this is 0.3. So uh, so dividing these two delta lambda by delta tubular, so 5.48 REX minus 0.5 divided by 0.37 REX minus zero point 0.2. Okay, so here it will be minus zero point 0.5 minus plus zero point 0.2. This will be REX minus zero point 0.3. So this is zero point 0.3 and this is 0.37, this is 5.48. So REX is equal to minus zero point 0.3. So REX is equal to the 441426 is the 441446 is the critical Reynolds number at which transition occurs. Next, in a capillary tube of radius r is equal to 0.25 mm, a fully curved laminar velocity profile is defined as u is equal to r square divided by 4 mu into curly p by minus curly p by curly x 1 minus r square by r square bracket close. In the expression minus del p by del x is equal to 1 megapascal per meter, mu dynamics is the dynamic viscosity of fluid, and gamma and R is the radial position of the center line of the tube. If the flow through the tube is if flow through the tube is 1000 cube per second, the viscosity of the fluid in meter per second. So here Q is your here U is this equation, okay, and del P by del X is your this, okay, and we have to find out the viscosity. We have to find out this mean, and uh, if load and flow rate is your 1000 cube per second. Okay. So we can find out velocity as radius is 0.25. So we can find out mean velocity. Okay. So this mean velocity is Q by A. Sorry, Q into A. Mean velocity is Q by E. Okay. So this is 5.09. Okay. So and this is the mean velocity and maximum velocity in case of laminar flow is. So this is the laminar flow fluid plus laminar flow. So mean maximum velocity is your mean velocity to 2, that is 1.4, and maximum velocity to x when radius is 0. So for radial distance is 0. Okay, so this will be 0. So this will be the point of maximum velocity max is r square by 4 minus. So this is your maximum velocity. Okay. So del p by del x is your minus 1 mp. Okay. So it is minus w by 1. So putting the value Umax we have, okay, and W by dx we have, R we have, so we can find out this mu is here 0.0153484 Pascal second. Okay. Next, the spin friction coefficient of a turbulent pipe flow is defined as Cf is equal to tau W half rho V square, where tau W is the wall shear stress and V is the average flow velocity. The value of Cf is empirically given by the relationship Cf is equal to 0.065 2 by Re raised for 0.25. Where R is the Reynolds number if the velocity is 10 meter per second, diameter of pipe is 250 mm. Economy of storage equals to fluid is 0.25 into minus 6 meter square per second. The density of fluid is 700 kilogram per meter square per meter cube. If the spin friction drag induced by the flow over the length. So here CF is shear stress by half rho distance. Okay, CF is this. Okay. And this is in terms of velocity. Okay, and small shear stress. And CF is another form is in terms of normal is this. Okay. If the average low velocity is your 10 meters, so we is 10 meter per second, and diameter pipe is 50 mm, and so and other it is so we can find out velocity is given. Velocity is average velocity 10 meters per second, and diameter is 250 mm, and density is 700, and this kinematic viscosity is 0.25 meter per minus 6. Okay. So this is your RE is equal to rho VD by mu. So VD by mu. So this is 10 into 0.25 divided by mu. So this is the roll number here, 10 plus 7. And from this, because it is only the function of the roll number, okay, so and we can find out roll number like this, and we can find out CF. So CF is your 0.00137. Okay. Now this is question number one. Here rho is known and V is known, V is also known. Okay. And now CF is known, so we can find out shear wall stress. Okay. So shear wall stress is here 4.811 because all the countries are known. Okay. Now shear wall shear stress is nothing but uh, tau W into area parallel to the shear stress that is pi d. So these these here these given L is a 1 meter. Okay. So tau W is known, so we can find out 37.76 meters. Next, a 150 mm into 150 mm square pillar is located at a river in a river with water flowing at a velocity of 2 meter per second as shown in figure. The height of the pillar is 8 meter. Take density of water as 1000 kilogram per meter cube. Kinematic viscosity as 1 meter to minus 6 meters per second square. Coefficient of drag of the pillar is 2. The drag force exerted on the pillar is so this is the pillar shown. Okay, this is the and the velocity is 2 meter per second. So drag force is nothing but rho A U square into CD by 2. Okay, so here A is there. This is 8 into 150. Okay, and rho is just 1000 for water, and U is 2, and CD is 2. So this is drag force 4800 meters. Okay, next. An modified plate is used to measure flow rate of air density 1.25 kilogram per meter cube in a duct of 50 mm diameter as shown in the figure. The volume flow rate is 1 meter cube per second. Flow at section 1 and 3 is uniform and section 2 is located at Venal and Katta. The diameter ratio of dt by d1 is 0.66. The flow area at Vinagantakta A2 is equal to 0.65 AT, where AT is the area of orifice. The pressure difference between location 2 and 3 in Newton per meter square is. So this is the diagram given. This is location 1, this is 2, this is 3, this is this is equal to given. It is equal to 50 mm, and it is uh, given. This is ratio is given. Utility by given ratio is given. Okay. Now an area and Vina contractor is formed here. Okay. So and A2 by 80, A2 is the area of Vena Contracta, where the density is your 0.65. Okay. So A2 by 80 is your 0.65. So, and theoretical discharge is that one. So, and theoretical discharge is given. Theoretical discharge is given one. So discharge at as this area ratio is your A2 by A80 is your 0.65. So as the ratio is area is so the discharge at Vina conductor is your 0.65 and area is also reduced by 0.65 because of this area contraction. Okay. Now the now the area at this section is your according to 250 mm. Okay, and at as it is by this D1 is your 0.66. Okay, so this the discharge at Bina conductor is 0.65 and this is your here it is this area ratio is your area at section 2 is your 0.65 into this. Okay, this 80. So this is the area of 80. So the velocity at Vina contractile we can find out. Okay, so the velocity at Vina contractile is 46.79. Okay, so velocity at section 3. Okay. The same discharge will go to this. So the velocity at section 3 is your 0.65 divided by area of this. Okay, so the velocity at section 3 is your 13.24. Okay, so at Vina contractor the charge has been reduced. Okay, so actual discharge is 1 and here the discharge is just 0.65. Okay, so here the discharge will also be remain just 0.65. Okay, so now we have velocity at this 3. Okay, and this velocity at this. Okay, uh, so applying sorry velocity at 2, we have velocity at 2 and velocity at 3. So applying Bernoulli's equation between 1 and 2, between 2 and 3, so it will be b2 square by 2d, b2 by 2d, and b1 this cable to the input to the okay. From this we can have pressure difference. Okay. P2 and P3 are known, so we can have P2 by P2 and P2, P2 and P2 is there. Okay. 1, 2, 3, 8, 1, 2, 3, 1, 2. So, the most important uh, fundamental in this question is that here the discharge is 1 meter cube per second, but here the discharge has been reduced by an amount of that beta content. Okay, 0.25. Okay, and here when the discharge at 2 is 0.65, so here the discharge is also same. Okay, so answer will be according to that. Okay, that is all about question paper XC 2018. Thank you very much.